So for those of you who weren't here yesterday in the packet, you might watch the video that's on you. Make sure that we know our general rules. Jillian, what's the first rule for drawing any Lewis dot structure? Okay, so counting these valence electrons, CH2O. Everybody, how many valence electrons does that represent? So carbon has 4 because it's in group 4. Each hydrogen carries 1 because it's in group 1, and oxygen's in group 6, so that should be 12 valence electrons. Just making sure we are seeing that it's just the group number. And then Taz, what's the next step after we count valence electrons? Okay, so who's likely to be center here? Why carbon? Right, stuff's in the center, it's sharing a lot, so it needs to have a low EN. So carbon will be in the middle, and then you're going to attach the ligands. Ligand is the name for the attachments that's provided, or that are the other atoms attached to the central atom. So we want to make everything as symmetrical as possible, so there's kind of a balance within the atom, or within the molecule. So I'm going to put H's, well, I'll draw it probably like you guys. You're probably doing like north, south, east, west kind of drawings. So you probably put 2 H's on the left and right, and then an O either on top or bottom. Okay, so we get that far. How many electrons have we used? Okay, so V, valence electrons, S, skeleton, E, add electrons into an octet. So naturally that would be just adding lone pairs. So you probably put lone pair, lone pair, lone pair, lone pair, making sure everybody has octet, except for hydrogen, who attains what? Duet, right? Okay, so we've technically followed the rules so far. Now the P means like, do I need to repair anything, and I need to look to revise, possibly based on how many electrons are here. How many electrons are present so far? 2, 4, 6, 8, 10, 12, 14. Oops, too many, right? So what do we have to reconsider? Right, so I have lone pairs in different places. Instead of giving carbon a lone pair and oxygen a lone pair, what can I make them do? Share through a double bond. So if I erase the lone pair here, I erased 1 lone pair here, I've taken off 4, which drops me down to 10, and then I'll just double bond that. So they're sharing instead. So how many are here? How many electrons are here? 12. Okay? So that gives us the opportunity to see how we can revise after the fact. Yeah? Nope, so or C, H, H, O like this. So basically this can rotate in space anyway. This does not affect the drawing itself. It's still the same exact Lewis structure. Okay, so think about what this looks like. We have a central atom. These ligands all want to get as far away from each other as possible. What would be the what would this look like if the C's or the CH and the C double O bond could get as far apart from each other as possible? Say again? Trigonal planar. It is trigonal because it's got 3 legs and they're all separated out into a triangle shape. And it's planar because planar means like a plane, a flat plane, like a 2D shape. Because there's no distortion effects by any lone pairs on the central atom. Only the lone pairs in the central atom will cause it to go 3D, will cause it to be shifted. So this is trigonal planar. And I'm going to stretch your mind on bond angles here, okay? If I am a trigonal planar structure, it doesn't really look like this. It looks more like this. And if I'm looking at this like a circle cut into 3 equal pieces would be what bond angle here? 120 degrees, right? That's the same bond angle here, and approximately the same bond angle here. Now, technically 120 would probably be this hydrogen to hydrogen one. This double bond might shift it a little bit, but we approximate everything to try to keep our numbers kind of simple. So that would be the bond angle for a trigonal planar structure. We good? Okay. So carbon dioxide, and then sulfate. So how many electrons in carbon dioxide? 16. Who's your central? Carbon. What do you do with the others? Either side, top and bottom, just make them symmetrical as possible. OO. And then what? Say again? Your next thought is to add what? Octet across the board, right? Because nobody has octet yet. So your thoughts would be dots, lone pair, lone pair, lone pair, lone pair, lone pair. Now, obviously, I'm going through every single step. you guys are probably going, okay, I can count how many lone pair are going to be there. I can count how many electrons. I know that's more than 16. How many is this? 20. So you don't have to go through the process of like, let me add 8. Oh no, got too many. Revise, because you're going to have to do that for a lot of structures. So as I take away a lone pair from oxygen and from carbon, what am I doing? What am I telling them to do now? Share, make a double bond. Okay, so that helps out 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so still have too many, so it also has to happen. Double on the other side. So I take away a lone pair from carbon, take away a lone pair from oxygen, and say you guys share. So this one has 2 double bonds. Now, the central atom is the guy who we look at for molecular geometry. What is the molecular geometry around carbon? Linear, it's a straight line, right? There's only one way you can connect these 3 atoms when there's no distortion effects from any lone pair on the central atom. It's like atom bonded to atom bonded to atom. It's a linear structure. So what would the bond angle be between this carbon and oxygen and this carbon and oxygen? What is it? 180, and that's just because it's a hemisphere, right? It's half of a circle. So you're getting bond angles a little bit? Okay. What was the next one? Sulfur dioxide? Sulfate? Okay. So we're going to talk about this one with regard to formal charge in just a second. I'm going to see how you guys drew it first. Okay, so take a second if you're still not done. Maybe I need to mention this. What do I do with the 2 negative charge? Add 2 more electrons to your valence count. Planar, we're going to work with the geometry a whole lot. Planar would be a flat structure because there's no lone pairs on the central atom. Lone pairs on the central atom start to cause like repulsion, which means like not a planar structure. Alright, so how many people have this like this so far? Single bond of those, okay. As you add your electrons, where are you adding them? To those, 1, 2, 3, lone pair, lone pair, lone pair. Okay, how many electrons are on my structure? How many? 8, you can do this. 16, 24, 32. So check, technically I have a valid Lewis structure according to our rules so far. I'm going to tell you this is wrong. This is wrong because the formal charges do not agree with the rules of formal charge. So let me show you that on the next slide. We'll come back and we'll revise this and talk about why this does not work. Okay? So we'll come right back to that. So leave it there for a second and we'll talk about why this matters. Okay, so what we're considering is that, you can draw a Lewis structure. As long as you get 1,300 electrons and every electron in that, it seems pretty valid. But what we have to consider is that sometimes it's not valid based on the rules of formal charge. So the formal charge is what we look at to evaluate the validity of a structure. So on the sulfate one, it was obvious that sulfur was in the middle. But on other ones like nitrogen or dinitrogen monoxide, it's not obvious who's in the middle. Because if I'm looking at dinitrogen monoxide, who would you consider putting in the middle first? A lot of you are saying oxygen because it's a singleton, right? But if you look at oxygen, it's more electronegative than nitrogen, so you're not quite sure like who's going to be put in the middle. So you have to consider formal charge on a number of like probably 3 structures, and then go, okay, who's the best one out of 3? So like dichlorine pentaoxide is actually another one that's kind of difficult too. So we're going to look at validity of structures based on formal charge. So your rules are, and the highlighted stuff is what I think is important here, okay? So your rules are, if you're trying to calculate the formal charge on a single atom in a Lewis dot diagram, you first think about the number of valence electrons the free atom has. You would do that just based on the periodic table. Oxygen has 6, fluorine has 7, carbon has 4. It's just whatever the PTOE says. And you would subtract that from the number of electrons you have assigned it in your structure, in your Lewis dot diagram. Now the word assigned I've defined kind of down here, but essentially that is in a bond, like a S to O bond, the number I have assigned to sulfur is half of that bond. So I've assigned 1 electron to sulfur in that single bond situation. And then if sulfur, let's just say it had a lone pair, the lone pair would be 100% assigned to sulfur because it's not sharing it with anybody. So in this situation, I would have 1, 2, 3 assigned to sulfur. So the assigned is the number of non-bonding electrons, aka lone pair, and half of the bonded electrons, which because it's sharing it with another one. So what you do is you take the valence electrons it should have based on PTOE, you subtract the assigned based on the model drawing, and that is the formal charge. Formal charges can be positive, negative, and 0. But what we're looking for is we want everything to be 0, unless there's an example like sulfate. But we want everything to be 0 because that eliminates all charge repulsion. It makes a very stable molecule. If you have more valence electrons than it normally should have, you have more electrons, that makes you negative, right? You have just more negative things. If you have less electrons assigned to you than you should have, it makes you a positive charge or a positive formal charge. And then if you have an equal amount to what you should have, you have a 0 formal charge. So the most favorable or the most valid Lewis structures have a formal charge of 0 for each atom. How many thumbs up when you go to this? I have a couple more rules on the next slide. We want 0, but if we have like a positive and a negative formal charge someplace, we want to keep those stable. We want to keep them far apart if they're both negative and both negative, or both positive, or we can keep them close to each other if they're opposites in charge. That's going to be our next part. I'll come right back to that. So for cases where you are trying to figure out who's the most favorable or the most valid Lewis structure, this is kind of your set of rules. You want small numbers like a -1 or a +1. You don't want like a -4 or +4. That would be a stupid high formal charge. Preferably 0, because that's going to give us the most stable structure. Like charges are close to each other. Unlike charges are, yeah. So unlike charges, so like a positive and a negative can be close to each other because they would attract, like positive and positive. You don't want them close to each other because those would repel like a negative and negative would. Generally, the electronegative elements are getting like a negative formal charge if they have to have one, because they are electronegative, so they do kind of pull electrons towards themselves. That would make them more stable. And if you have a total, when you sum up the formal charges, it should equal the like polyatomic ion charge, and that would show you that you have assigned them in an appropriate way. A lot of little rules, but once you like do 1 or 2 examples, it makes sense. You with me? Yeah. All right, and take just another second to finish up those rules. Go back to sulfate. And let's count the formal charges based on how it currently is drawn. So here's our sulfate. We've got single bonds all the way. So what we want to look for is what should sulfur have, our sulfur and oxygen, and how many are technically assigned to it. So I usually just, I'll make a little chart of formal charges. Here's my sulfur one. How many valence electrons should sulfur have, based on what its periodic table says? 6, right? We're going to take those that it should have, subtract the ones that it has been assigned. Remember the bonded, how many do you count from a bonding situation? Just half of it, so 1 of them. So that's 1, 2, 3, 4. 4 have been assigned to it. So sulfur's formal charge is a +2. So I'm going to put a +2 next to sulfur. Oxygen and all these oxygens are exactly the same. So each of these oxygens should have 6 valence electrons assigned from the periodic table. But according to how this is drawn, I have 2, 4, 6 from the lone pair, plus 1 from the bonded pair, so it's how many? 7. 6 minus 7 is a negative 1. So each of these oxygens here, all the way around, have a negative 1 formal charge. All right, so you've already seen that we have a positive 2, which is getting kind of high, and we got all these negatives. So nothing is 0. So this is not as valid or not as stable as it could be. So what we want to consider is how can we rearrange this a little bit, still maintaining our 32 electrons to minimize our formal charges. Any ideas? Why double bonds? Why can sulfur get more electrons? One of the exceptions, right? So phosphorus, sulfur, chlorine, and down, those are in the 3p energy level. They have access to 3d orbitals. They're like extra pockets for electrons that they normally wouldn't need, but they can use them if they need them because they're in the 3rd energy level. So I'm just gonna I'm just gonna draw this again. Okay. So what we're gonna do is reconsider. Can't write with that. How we draw this. So we know that I'm gonna have to put lone pairs on these oxygens no matter what. So I'm gonna put 2 on each one. And then let's think about what else I could do. Because I want 32 total. Okay. So if I put a double bond on one and a double bond on another, both of these oxygens have octet. Sulfur has more than octet, which is totally fine with. Okay, so I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. What else do I need? 2 lones, right? Okay, so there's my 32. So everybody has octet, right? Now let's double check formal charges. Sulfur has what? 6 from what it normally would have. Subtract 1, 2, 3, 4, 5, 6. I'm counting half those bonds. So that's 6 minus 6, which is 0. Yay, has a formal charge of 0. And then oxygen's here. Let's do the double bond ones first. Oxygen has 6, subtract what? Okay, good. 6, 2, 4, 6, because I'm counting half of the double bond. So those oxygens have a formal charge of 0. Okay, so there's 0, 0, 0. And then what do these oxygens have a formal charge of? Same as earlier, right? 6 minus 7 is equal to negative 1. Okay, so look, the negative 1s are far apart from each other, so there's limited repulsion. And I've got some zeros going on, so this is looking pretty valid. And then what I should remember is sulfate has a negative 2 charge. What should the formal charges add up to be? And do they? Yes, right. Negative 1 is equal to negative 2. One extra thing that has to be drawn on any polyatomic is a bracket, and you put your negative 2 charge up here. Now, you don't always have to write the formal charges out, but you should be able to calculate them very quickly. Question? No, you don't have to write the zeros or the negative 1s on the structure at all, but you should be able to calculate them, or you can need to make a list, or if it says, like, what's the formal charge of sulfur in the structure, do it, and then don't forget polys have a charge from them. All right, let's try another one. Actually, do me a favor. 1 second. Can this top room go grab their laptop? And then you guys will go next. What's up?
Can we draw like resonance structure? So we like.
Can we draw what?
Like resonance structure.
We're gonna talk about. We'll talk about that in just 1 second. Yep. Mm-hmm. We're gonna practice with formal charge and just some more here. Next half, people, go grab your laptops. While you're waiting, write down what's on the board. You do not have to write everything that's on the board, but write down some of it. And just get to my website when you can. So go ahead and get logged on computer. They take a minute, and I'll go ahead and teach you resonance and isomers before the back to formal charge. Alright, so resonance is not something you maybe learned a whole lot about in honors chem, but essentially it is the same exact structure like structure 1 and structure 2 and structure 3, no matter how many of them you draw that are resonance with each other, they're all the same structure. It's just you simply place the electrons, either a lone pair or a double bond or something like that, you've placed it in a different location. But it's still the same because they're actually superimposed on each other. They're all the same structure. I'm going to show you an example of that in a second. So the connection, meaning like the skeleton is the same, the atoms are placed in the same location, but where you place the electrons or the bonding or the lone pairs are going to be placed in a different location. So that is the premise of what what resonance means. Atoms in the same place, electrons in different places. Whenever you have multiple resonance structures, or Lewis dot structures that are all valid, to show that they are resonating with each other, they're called resonance structures. You draw a double-headed arrow between them with a bracket around the entire slew of Lewis dot structures. So for that sulfate one, try to draw this kind of small. It's teeny tiny here. Sulfate, okay. So I decided to put the double bonds on the top and the bottom oxygens. You put a double-headed arrow between that and the other sulfate you could have equally drawn, which is double bonds on the left and the right. It's teeny tiny, sorry guys, but I think you're seeing the purpose of this. And there's sulfate with the 2 negative. Okay, so I'm saying that these are resonant structures of each other because they're both exactly the same. It's just the double bonds placed in a different location, and they are both technically correct. And I put a big bracket around the whole thing and put a double-headed arrow between them. So truly what's happening here is that the double bond is neither here nor here nor here nor here. It's equally spread out between all of the bonds, which complicates things. So I would normally call a single line a single bond. I'd normally call a double line a double bond. But what happens is the line, instead of being drawn as a double bond like that, we draw it dashed to indicate that the double bond is not here, 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 here. It's spread out equally amongst all 4 bonds. Okay, so what happens when I have 6 total bonds, right? So 2, 4, 5, 6. 6 bonds spread out in 4 places. That's 6 over 4. Okay, what's 6 over 4? 3/2, which is 1.5. The bond length and strength is stronger than a single bond, but not as strong as a double bond. Okay, so this is a 1.5 bond, which is that stronger or weaker than a double bond? Weaker. So is it longer or shorter than a double bond? Longer. So what you're having to see, and you probably saw this on some of your homework, it was like bond length, and you're ordering them based on smallest to longest bond length. You have to start thinking about resonance structures and if they apply in that situation. Here we have one. So this is a single bond. This is a double bond. So this is weak or strength. A strength comparison here. The single bond is weaker than the 1.5 bond, which is weaker than the double bond. Question? No? Okay. Let me scroll down and we'll show you a little more here, okay? So what I was just mentioning is that since this double bond, or these double bonds are spread about the molecule equally, we call that a superposition. The entire molecule has kind of meshed into a single molecule, which we don't really draw. We draw the resonance structure instead. So this is benzene, C6H6, and you can see that you've got a double, 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 single, 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 and then what's happened here? They've just switched places of doubles and singles, but what we truly draw here, this is like organic, we draw this to indicate the double bonds can kind of be in any arrangement around, not next to each other, but like this or this, but instead of calling it a double or single, we put a circle to indicate that it's a blend of bonds. You're looking at me like I'm crazy. We'll work with this a lot more, okay? So what you should know is that this is an intermediate in length and strength to show the difference, like I've indicated here, between a single bond and a double bond in a 1.5 bond. So let me draw another one. Yeah.
Will you always assume that each bond's 1.5?
No. So that's what I'm going to show you. Let's do nitrate. I think I might have that on the next slide. No, let's do carbonate, not nitrate. Okay. So carbonate, CO3 2-. Give me the valence electrons. All right, so be with me, okay? I know you're trying to get to my website still, but be with me, okay? Valence electrons. So 4 from carbon plus 18 total from oxygen plus 2 on 18, 22, 24. Is that right? Okay. And then carbon's in the middle. And oxygens are going to kind of take their places. I'll do it just symmetrical as I can. What you'll notice is we start adding electrons. Let's get to octet on everybody. Take a minute and let's figure out what we need, okay? I'm not going to draw and erase. This one was on last year's exam, year before, and so many people got it wrong because they could not explain what a resonance structure was, or draw multiple structures that were the same. I was sad, but yeah. I think my students do okay then. All right, so what are we looking at? What kind of bonds? One double and singles. So that's, yeah, 1, 2. So 6, 8, 16. Okay, so we got 24 here, right? All right, so I chose to put the double bond on the very left, but where else can I put it? On the top, and then on the side, right? So before we move on, count out formal charge for each of these. You don't have to write it out, so let's just talk. Carbon should have how many valence? 4, how many is it assigned? 4, 0 formal charge. Oxygen should have 6, it has 7, so 2, 4, 6, half of that one, 7, so it has a -1 formal charge. This is the same thing, it has a -1 formal charge. This has a 0 formal charge. So this is a -1 and a -1, overall giving us a -2, which is carbonate's charge, so we are in good shape. And that is about the only way you could draw this, because carbon cannot expand octet, so it really can't do anything else but double bond, single bond, single bond. So we're going to draw the resonance structure, double bond up. And then carbonate with the double bond on the other side. Okay, so now we have the situation where we're going to talk about bond length and strength again. So I have a double bond that's not truly in any of these positions. It's superimposed across all bonds. So that's extra bond. That extra bond is going to be equally distributed between these 3 locations. Okay, so there's 2 ways to think about this. I have 1, 2, 3, 4. 4 total bonds distributed in how many locations? How many locations? 3. Okay, so I have 4 bonds distributed in 3 locations, which gives me 1.33. Okay, so I have a bond length of 1.33 on all of those locations. So this is the bond length and strength kind of determiner. So let's talk about how that falls in a line of like other bond lengths and strengths. So a single bond is weaker and longer than a 1.3. Actually, you guys tell me, would a 1.5 or 1.33 bond be weaker? 1.33, right? Because it's towards the one side, not the 2 side. And that's weaker than a 1.5 bond, which is weaker than a double bond, which is weaker than a triple bond. And so you can arrange that in order of length and strength based on your comparisons. We'll do that a little bit more. Okay, yeah.
Would you have to move it so it would be a double bond like a bond?
No, because it's the same. That's the same situation as this one, or this one, or this one. These are all rotating in space freely. So I would not try to draw this in any other way that would still correlate with one of these. Okay. All right. So that's another resonance structure and bond length and strength comparison. We'll work with this a little bit more as we go throughout the unit. Okay. Go to my website under homework. I'm still not done with other stuff. I'm gonna leave this up here for you. We're gonna have what license. But I'm gonna give you a second to just practice the formal charge a little bit more. Under homework, there should be a link that says classwork. I think it was under yesterday's, because I was supposed to do it yesterday. Is it today? Okay, maybe I moved it. So it's under yesterday. It's under yesterday. It says formal charge in big caps. I just want you guys to take a minute and look over that. You have to look at the whole thing. Let's see what you think about that. So just try a couple, see what you can figure out formal charges of. Even if you just go through the structures and you're like, okay, I can do the formal charges, I'll leave them. Good. Oh, sorry. I paused it earlier.